A very good afternoon to the chair of this coastal dynamics and modeling session and distinguished participants. I would like to welcome all of you to my presentation on assessment of drainage performance of selected polders in types of climate change using mathematical modeling. And this is Dipen Saha. I'm working as a junior specialist in IWM, and other co-authors of this research work are Maisha Samia Khan, MD Arifur Rahman, MD Raju Ahmed, Sheikh Mahiduzzaman, and MD Saiful Islam. Among other co-authors, Mr. Arifur Rahman is present here along with me. This is the outline of my presentation. Next couple of minutes, I'll be talking about characterization of study area, then profile of problems, and then approach and methodology. Under approach and methodology, I will be discussing about drainage model framework, climate change, and model setup, and then polder inundation mapping and risk analysis. And finally, I will discuss about improvement options and effectiveness of the selected polders. So our coastal region can be subdivided into 4 categories, and these are Southwest, South Central, Southeast, and Eastern Hilly region. Each region has unique characteristics or some common characteristics, like Southwest region receive very little freshwater flow, and in the southern side of this region is protected by Sundarban, and so the inside the polders located inside this region are a bit protected from storm surge, and this area is facing a huge tidal action, and the erosion problem is also there, and the polders are facing prolonged waterlogging. And the south central region is vulnerable to storm surge and erosion, and it is vulnerable to erosion, and waterlogging problem in the polders are also seen here. And the southeast region is also vulnerable to storm surge, and this area are subjected to prolonged waterlogging due to encroachment and land reclamation by closing tidal creeks. And this region is also very morphologically active place, and land accretion is dominant than erosion. And last of all, eastern hilly region is vulnerable to storm surge and prone to flash flood due to steep gradient of rivers and intense rainfall. This is our study area, and we have selected 5 folders in 4 regions. Folder 15 and 29 is in Southwest region, and folder 40 by 1 is South Central region, and folder 59 by 2 is in Southeast, and last of all, 64 by 1 and 1B is a cluster of 2 folders. You consider 2 folders into 1 folder actually, and it is situated in the Eastern Hilly region. And now the problems of the polders. Polders are actually constructed in early 1960s by Bangladesh Water Development Board to protect the area from tidal flooding and salinity intrusion, to boost up agriculture activities inside the polder, and that time control structure like regulator are constructed along the peripheral along the embankment also. Over the time, the condition or functionality of the control structures has been deteriorated, and waterlogging problem are seen inside the polder, and the design has been carried out that time without considering the climate change. And now we are seeing the impact of climate change, and we are seeing the waterlogging problem inside the polder. So waterlogging problem is a consequence of sedimentation and siltation of internal coal and the peripheral river and the dysfunctionality of constant structures and the insufficient amount of bridge and culvert in the road alignment inside the polder, um, and the um, lack of institutional arrangement for gate operation, etc. So other problems are also there in the polder, like erosion, salinity, intrusion, etc. We will just be concerned with waterlogging problem, and we will try to address this. So to solve this issue, to solve waterlogging problem or water management inside the polder, we need drainage model. Why we do need a drainage model? To assess the drainage performance, it helps to depict a flood condition for different scenarios, to assess the infrastructure requirement for water management, and we can assess damage due to the inundation inside the polder, and ultimately it helps to prepare investment plans in the polders. Conduct a study or a research work, first of all, we need a good quality data. Our model result entirely depends on the quality of our data. So we primarily we collected river and cross-section, water level data, and topographic data and structure information and embankment alignment for drainage model, and for secondary data we used rainfall and evaporation, which has been collected from BMD and Water Development Board, and we have 3 regional models like Southwest Regional Model, Southeast, and the Eastern Hill Region model that have been used for this research work. And after collecting data, we had to do a lot of data analysis for study purpose, like rainfall trend analysis, maybe elevation curve, dam of polder, and structural inventory preparation, frequency analysis, etc. These are the part of the study. So this is the simple flowchart of our modeling work. Actually, the drainage model can be drainage model is a combination of 2 models. One is hydrological model and another one is hydrodynamic model. So hydrological model is nothing but a rainfall runoff model, and which is also known as the NAM model for mic users. That means the net bore storming. It's a Dutch word actually. And we are using mic packages from DHI, which is a very reliable, commercial, and powerful modeling tool. So for rainfall runoff model, at first we have to delineate our catchment. Catchment is delineated based on the topographic data, road network, and color element, and land slope, and then we have to provide the soil characteristics, and we have to prepare a rainfall runoff parameter file, and then finally we simulate the rainfall runoff model, and we'll get a result file. And in rainfall runoff result file, we actually get the CAL wise runoff. Actually, in every outlet of the CAL, we get a runoff from rainfall runoff result. And this result file is used in 1D hydrodynamic simulation. So for 1D hydrodynamic simulation, we need alignment and cross-section of internal culls of the polders, the alignment of the culls, which is actually a network file, and we have to prepare a cross-section file, and we have to give information of control structure like number of bend number, bend size, and sea level, condition of operation, etc. And we have to provide a boundary file, and we have to provide a HD parameter file where Manning's number of the channels are to be included. So after incorporating all these files in the simulation file, we run the hydrodynamic file, and we will ultimately simulate the drainage model. And what we get in the drainage model result file, that is simple water flow, water level, and water velocity time series. By this result file, we prepare flood inundation map, and, and we take decision for the management of the water management of the polder. So IW do have 6 regional models. These are Southwest regional model, Southeast regional model, Eastern Hilly regional model, Northeast, Northwest, and North Central regional model, and one is general model. So in Southwest regional model, actually, our polder 29, 15, and 40/1 are located. So these 3 polders have been integrated into the Southwest regional model, and we simulated the whole regional model for this polders. All the call network are integrated in this model, and the upstream boundaries in the Southeast regional model is Goravari and Borobaja, and the 13 downstream boundaries, which are actually essentially water level, and the upstream boundary are discharge. So in the Southeast regional model, we actually did a dedicated model uh, of a 59/2 polder, which is located in Southeast regional model. The upstream boundaries and downstream boundaries have been taken from the Southeast regional model result file, and similarly, a 64/1 is a part of region model, and the boundaries are taken from here. For this polder, we have also did a dedicated model. And after simulating the drainage model over the monsoon period, and we calibrated the model as well, and the simulated result and the measured water level fits very well at satisfactory level. We calibrated in different location. We have validated the model against water level and discharge as well. And this is the sea level rise which has been taken, and this is actually absolute sea level rise for RCP 8.5 for the projection 2050, and we have taken a 0.2 meter sea level rise for the year 2050, and we used it for sea level rise condition or climate change condition. And climate change for climate change rainfall intensity will be also changed, and we for 2050 projection we took the high value, and in the southeast region for polder 15 and 29, the percentage of change in rainfall will be like this, and the temperature change will also be incorporated because in the rainfall runoff model we need evaporation on data, so we'll change the evaporation data accordingly. If we get the temperature change by Feynman equation, we can easily change the evaporation data, and by simulating basin model, we can change the upstream, we can estimate the changes in upstream flow, and the changes in the Bowdler path is like this for 2050. And for land subsidence value, we have taken this value for each polder for accurate result, and this lesson subsidence values has been taken from the from a report from a long-term monitoring research and analysis of Bangladesh coastal zone of IWM project, and this is another separate study, but we used only the values from here. And we have developed different scenarios for inundation map or see the flood map, like its existing condition of existing condition of Kal, peripheral river and drainage structure and hydrological condition of 2019. 2019 actually was our base year, and design hydrological condition is one in 25 years return period rainfall event imposed on existing condition. And in climate change condition, climate change projection for the year 2050, we RCP 8.5 scenario is used, is imposed on design hydrological condition. And last of all, we we observed the improved condition. Improvement measures called excavation, regulatory modeling, etc., applied on existing drainage system to simulate climate change condition. This is the inundation map for Polder 15. It is an existing condition you see in the left side, and the climate change condition in the 2050 projection. So you can see here the climate change condition is always worse than the existing condition. And the flood map is here for different time step. So to make a decision, we need actually one flood map. We consider one flood map. So which flood map in which time step we have we have to choose, or how we had chosen the flood map for our analysis. In this graph, we can see that we simulated for a long period, like a monsoon period, a drainage model, and then we find the minimum values in consecutive 3 days, and from that values we chose the maximum values. That means at least 3 days this water level is maintained in the Khal. So in the graph you can see 3.35 is that value. It's just sampled for understanding. So now after getting this value, we generate the flood map using GIS tool, and we take the decision for improvement. So now the exposure vulnerability and risk analysis. So for Polder 15, the inundation free area is 15%, and the flood and design had climate change condition, the flood free area is 9.82%. The area is reducing because of climate change. And using this inundation map, the damage assessment can be done by Fiat. This is another technology. I'm not going into this. And this is for Polder 40/1, and the inundation free area is 68%, and the climate change condition here 47.02%. And for Polder 29, the flood free area is 36%, and flood free area is 16%. And so we can say if Polder is free from inundation when the flood free area is 80%, and our target is to achieve 80% flood free area. And this is for Polder 15/2. This is flood free area is 88%, and flood free area is 67%, and Polder 64/1 and 1B. The flood free area is 72%, and the flood free area is 59.92%. And then we developed some improvement options through discussions, meetings, and workshops, field visit, etc. And these options are at first our first option is sea level fixation with standard size regulator, and the option 2 is option 1 plus excavation of drainage canal and peripheral river, and option 3, if option 2 fails, we explore the option 3, and option 3 we just added the additional vents in the regulator, plus if a new regulator is required, we provide it. After improvement option, we have seen that flood free area for Polder 15 becomes 88%, which is quite more than 80%. So we can take the measurements, we can take the measures to improve the polder to that level, and interventions to to make this situation is we have to provide 5 control structures and excavation of 30 kilometer. And for the polder 29, we have to drain, we have to excavate 135 kilometer of canals and peripheral rivers and 15 control structure. We have to fix the sea level of 15 control structure and 6 additional vent we have to provide. And polder 40/1, and the flood free area, it is 7.6%. It is actually in option 2 we achieve this percentage, and the sea level fixation of 12 control structure with standard grade size, and excavation of all internal culls, like 37.5 kilometer culls need to be excavated. And for polder 59/2, similarly, we get 86.9% inundation free area uh, in improvement option. And we have to fix the sea level of 13 control structure, and 4 new control structure need to be constructed, and sorry, 4 additional vans, additional vans should be required in 4 control structure, and 9 new control structure should be constructed, and 190 kilometer of canals and peripheral river need to be excavated. And similarly, for 64/101B, we achieved 78.5%, as it is very close to 80%. And so the main interventions are 50 control structures we have to construct with new sea level, and excavation of 164 kilometer internal culls and peripheral rivers. So this is the bar chart of inundation free area percentage. So you can see for every polder, so the inundation free in improvement option is higher than 80%, except polder 29, which is 61%. In polder 29, we need palm drainage along with gravity drainage. So our research team has brought some innovative approach analysis for long-term polder management, such as increasing tidal plane and conveyance capacity of peripheral river, and innovation in material of gate, and increased vent size of drainage regulator and tidal river management and cluster of polders. We will discuss about only tidal plane increasement. So if we increase 200 meter at least the tidal plane and run the model, we got some interesting results. And the river system of polder 29 is Tekahori, Teligang, Salka, Lower Bhadra, Daluti, and Habarkhali Khal. And for 40/1, the river system are Bishkhali and Burishro River. And for polder 29, we see the for increased tidal plane, we saw the existing, we saw the increment in discharge time series, as well as positive discharge and negative discharge during flood tide or wave tide. And ultimately, the tidal prism of the river has been increased, which is a very important thing for the sustainability of a river. And increase of tidal, by the increasing of tidal plane, tidal prism has been increased 12% in Havarkala River, and tidal prism increased in 21% in Lower Bhadra River during the dry season. Title to our our I want to say that tidal plane is not available in all cases because there could be needed the land acquisition or if there is already a good setback distance, so tidal plane increasement may not be effective. So we have some way forward, mainstreaming the use of state-of-art modeling tools and systems in integrated planning, design, and implementation of water, river, and coastal zone management infrastructure. And we have to introduce some innovations like water apps, water management apps actually, and installation of palm drainage along with gravitational drainage, where gravity drainage system alone is not effective, and land use planning for each polder, considering cropping system, economic importance, social institution, hydromorphological and environmental conditions, and effective stakeholder consultations, and develop sediment management strategy and restore intertidal area and tidal plan if are possible, and network of monitoring system like water level, water flow, river bathymetry, sediment concentration, salinity, water quality, ecological parameters to generate data, information, and knowledge in case of emergency situation. And thank you for your kind attention. Now it's time for discussion. You can ask relevant questions regarding our research work or drainage model. I would like to address your questions. Thank you.